So this is the first video in our collection about axiomatic semantics. We'll start back at the beginning. We've covered some of this material in lecture, but I'd like to make this collection complete and cover all the material. If you want to skip ahead to the new material, please check the Moodle pages. The forum there will tell you what video to skip ahead to. We've seen the relevant reading. This really comes out of Tony Hoare's original paper on axiomatic semantics from the late 60s. This is a classic in computer science and in programming language literature. So you do want to read this. It's a very accessible paper and gives a glimpse into how things were done at that point in time. So we began this discussion by asking a simple question. Is this program correct? What about this program? We notice that there's just a small change. GCD1 is a disjunction. Here we have a conjunction with and. And so one of you very quickly pointed out that, well, what do we mean by correct? What does it mean for a program to be correct? And that's exactly what we want to get to in this discussion. And by correctness, what we want to do is prove that a program has a particular property. And so in this case, we have to decide that, well, there must be some property that makes this program the one we want. This one is not going to be the one we want. All right, so these correctness specifications, we're going to ask a couple questions. That is, what needs to be true before the program starts, and what should be true after the program terminates. So in the case of this GCD program, we see that there is a precondition, n0 greater than 1, m0 greater than 1. So when we begin, we're just requiring that these numbers are greater than or equal to 1. The code is the part in yellow in the middle, and the postcondition is the last component that says I is equal to the GCD of n0 and m0. So the precondition and the postcondition, these are mathematical statements. These are not computer programs. The yellow part in the middle, that is the computer code that we're trying to prove a particular property over. And so here what we're trying to show is that if this Hoare triple is valid, and if it's true, it tells us that if the precondition is met, if n0 is greater than 1 and m0 is greater than 1, this is true before the program begins and the program terminates, then afterwards I is equal to the greatest common divisor of n0 and m0. Right? So GCD here is not a function call. It's our mathematical definition of GCD. And so there's a proper specification of what that means that we all understand. But those are the two components in math, the precondition and the postcondition. And then the code in the middle. All right. So the point about termination is that partial correctness does not include a proof of termination. Partial correctness is a statement that says if the precondition holds and the program terminates, then the postcondition holds. If we want to get what's called total correctness, we then have to prove that the program terminates. And proofs of termination are a little different in structure than what we do for partial correctness. We may talk about this at some point, but that's not the focus of these discussions. So the form of these Hoare triples, as we mentioned, P and Q are mathematical expressions. The code then is the program that we're trying to prove correct, or the code snippet. So we're going to decompose the code into smaller and smaller pieces, and there'll always be some assignment, some statement of some form in between the pre and post condition. So the next question we'll ask is, which Hoare triples are valid and invalid? And so that will be the topic of the next video.